Thank you, Jim, for inviting me here. I was one of these femtosecond people trying to send an email to you accepting your invitation to come here. Yeah. So it's my first time in Singapore, and I visited.
Actually, you weren't quite femtosecond, you were more sort of picosecond.
Okay. Yeah, so it's a great pleasure to be here, and thank you very much for inviting me, and thanks for this crowd to putting all the resources here so that we can enjoy and discuss this very lively meeting.
The thing is, Tony, there's a chance that you're part of Spain might leave the EU, you see, so we thought we'd better sit together.
We hope not, yeah. I think we're better all together than just split apart, right? Well, okay.
We are with our science.
Yeah. So let me start my talk today, my presentation. So I'd like to talk a little bit about some of the work my group is doing here. This is ICIQ in Tarragona, and this is my outline today. So I'm going to start with a short introduction. I'll give a couple of short talks about, or short descriptions about ruthenium water oxidation catalyst, and then I'll move to one cobalt catalyst that can do both water oxidation and oxygen reduction, and I'll finish with conclusions and acknowledgements. So this is basically where everything starts up with Jim's structure, where he showed how the OSE PS2 work, and from outside, from synthetic inorganic chemistry, we were trying to design complexes that would mimic, in our case, not the structure, but actually the function of photosystem 2. We wanted to develop systems that could do water oxidation catalysis efficiently. So we're shooting for water splitting. So we call it artificial photosynthesis because basically the oxidation reaction is the same. We oxidize water to dioxygen, and instead of reducing water to carbohydrates, we do something that is much easier. It's just reducing protons to hydrogen. So basically, the key issues that we have been working with is trying to understand how these water oxidation catalysis work, and also those proton reduction catalysts. So if you go into the field of water oxidation catalysts, there are basically two completely different approaches that you can take and trying to generate water oxidation catalysts. One is the one we call the oxide approach. So there are a number of oxides that they can do water oxidations. And this, you can trace it as far back as 1902 when Cohen and Glasser were trying to calculate the redox potential of cobalt-2 to cobalt-3. And they found that there was a large deposition of cobalt oxide at the electrode and a huge electrocatalytic wave. And from the molecular point of view, the first well-characterized water oxidation catalysts were reported by Tom Meyer. That was 1982. So Tom Meyer had to wait like 80 years. He was 80 years behind the oxides, basically because he had to wait for coordination chemistry to be developed, right? Coordination chemistry didn't exist. And this is a picture that I found in the internet that shows pretty nicely how coordination chemistry has evolved over the last 100 years. So if you go back to something 1903, the beginning of the 20th century, this is Arrhenius got the Nobel Prize because he showed how chromium-2 could be oxidized by cobalt to make chromium-3. So, but basically, the way he was looking at things was like he had like naked cations that could be oxidized that could undergo redox reaction. And then 1913 came Werner, where he said, well, those metal ions are not naked. There is also a coordination sphere, a phase coordination sphere that is directly interacting with the metals, and this is when actually coordination chemistry started. And then came Henry Taube that got the Nobel Prize in 1983 and said, how are those electrons going from one place to another? How mechanistically, how these oxidation and reduction reactions occur? And this was basically the beginning of the outer sphere, inner sphere, electron transfer mechanism. But the whole picture could not be complete without the work by Professor Marcus, where he provided with a theoretical framework to all the oxidation reactions and electron transfer reactions. So with such a huge development over the last 100 years of the electron transfer and coordination chemistry, we thought that was a wonderful platform to try to develop our work and try to see if we could generate good water oxidation catalyst. So we, in the coordination chemistry, you have like large number of ligands, basically limitless number of ligands, and a whole bunch of transition metals at different oxidation states. So we thought that if you properly combine those ligands with these metals, you would be able to end up with powerful water oxidation catalysts. And actually, if you look at the turnover frequencies that we get with molecular catalysts, 1982, Tom Meyer got this blue dimer, which nearly needed 1,000 seconds to make just one turnover. And we recently we reported a catalyst that in 1 second makes 50,000 turnovers. So basically, means that we managed to increase the turnover frequency by nearly 8 orders of magnitude in basically the last 10 years. So this is a table with a graph that shows logs of turnover frequency, so how much faster a catalyst turns versus the year it was reported. And basically what is showing is this, over the last 10 years, basically there's a huge development of new water oxidation catalysts. So there's lots of information that have been brought to the community, to this particular field. So we learn a lot of how artificially how to make these new water oxidation catalysts, how to play with ligands so that you could lower down activation energies and make them work real fast. So as I mentioned, we basically we were interested basically in function, not in structure. And from a functional point of view, what you need to do for a water oxidation catalyst is basically from water remove protons and electrons, and finally end up making an oxygen-oxygen bond. This is taken from one of Holger's papers, where basically shows that after shining light to the different to the OSC, you just remove protons and electrons in a particular sequence until you end up making oxygen-oxygen bonds. So basically, what you need with a low molecular weight transition metal complex is to be able to basically do the same type of reaction, remove protons and electrons, and at some point when this is sufficiently activated, end up making oxygen-oxygen bonds. So I wanted to show you from an energetic perspective what is the benefit of this proton-coupled electron transfer, why this allows us to remove electrons and protons at relatively low potentials. So this is a discrete molecular complex. This is a carbon-ion bond. This is a carbon-ruthenium bond with a couple of pyritidyls and terpi and chloro. If you look at the electrochemistry of this complex, you can find the redox potential. The 3,2 is around 0.1 volt, and it's totally pH independent. There are no protons involved. You only remove one electron from this complex. If you want to remove a second electron and go to the 3,4 redox potential, then it goes all the way up to 1.1. So when you remove the second electron, you need lots of energy. So there is 1 volt difference between the 2,3 and the 3,4 redox potential. This is basically outer sphere electron transfer. You're only removing electrons from the metal center. But if now I'm going to change this ligand by a simple terpi, and I'm going to change the chloro by an aqua group, then I got these typical terpi BP Ru-aqua compounds that Tom Meyer described in the 80s. Then when I look at now I'm going to remove an electron, but also I'm going to remove protons from the Ru-aqua group. So now the potential is pH dependent, so the potential, the 2,3 potential decreases with pH. But if you look at the difference between the 2,3 and the 3,4 redox potentials, it's only 100 millivolts. So when I'm doing only outer sphere electron transfer, I'm building a lot of charge into the molecular complex, and I need lots of energy to remove a second electron. In the case of I can do proton-coupled electron transfer, I need only 100 millivolts. So the energy that it requires to go from higher oxidation states because of the PCET is much, much lower. So this is basically what in biophysics yourself, this is what you call it redox labeling, right? This is a way of removing electrons, a number of electrons and protons from a whole system without going to incredibly high redox potentials. So once you manage to make this first step of removing protons and electrons, then at some point you have to make an oxygen-oxygen bond. And you can make this in two ways from a phenomenological perspective. That's basically once you have a really high oxidation state, that means that to maintain such a high oxidation state, this oxo group or oxyl or whatever you end up here is going to have to give lots of electron density to the metal center. So this oxygen will become electrophilic and can undergo a water nucleophilic attack. So that's one of the ways that you can make oxygen-oxygen bond. The second one is a dimerization process. This is also in the literature called radical coupling, but I didn't like this name and we changed it to interaction of two MO units. The reason we put this interaction into MO units is basically because we look at the DFT of all the species that undergo this dimerization process, and they didn't look like a typical radical that you're used in organic chemistry. So so when you go to such a high oxidation states, at least with second row transition metals, then basically you have a distribution of electron density. You remove electron density from the metal, but also from the oxygen. So you have something in between what you would call a metal oxo and an oxyl.
Well,
so
you can call it oxygen coupling.
Yeah, that would be. It might be oxyl coupling or oxo coupling. So something in between that. So this interaction of two MO units that just encompasses the whole bunch of different options. So that I mean, this is just naming things, right? And yeah. Okay, so then I came out with this nice paper Holger just presented recently. And this is one third thing that we should always take into consideration when we try to build molecular water oxidation catalysts. And this is the liability of the ligands. If you are going to do water oxidation, I mean, you invariably have to use water. And normally we like to use 100% water, but if you use organic solvents or whatever, at some point you'll have to add water. So water is going to compete with your ligands there. So if your water competes with your ligands, it's likely that you're going to end up with the oxide instead of the molecule. And this is very beautifully shown by Holger and colleagues, where to maintain this manganese there at the right, to make the right Cuban structure, you need extremely rigid ligand framework. And that's what I think it's basically the message shown here. I think this also connects with the previous work by Theodore Akapi, that he needs these very rigid ligands to hold up all the metals there, because if you don't have rigid ligands, the whole thing can rearrange. So basically I call it this fighting ferro transition metal liability, which is basically what nature is doing. So this is basically my introduction. So now I'm going to go describe briefly one of water oxidation catalysts. This starts with a very nice collaboration we had with Li Cheng. Li Cheng sent us a really bright student, Lily Duan, to ICIQ, and we had a wonderful collaboration. So Li Cheng had published a nice paper on the BDA. We call it BP dicarboxylate, that is ligand that coordinates on the equatorial plane of a ruthenium metal center, and the axial positions we have a couple of periods. And basically what we show is that this complex could undergo several proton-coupled electron transfer process until you reach higher oxidation states. Here I call it ruthenium 5 oxo, ruthenium 4 oxyl, that's somewhere in between. We always talk about formal oxidation states. We know that we not are removing the electrons from the metal center, but from the MO group or ruthenium oxo group. But for keeping track of the number of electrons you're removing, I think it's easy to just use formal oxidation states. So once you reach such a high oxidation state, then we have a dimerization process that ends up making a peroxo, and finally this releases oxygen. And we show that by just changing the pyridine ligand, the axial pyridine ligands from ligands that had extended pi systems, this is like methoxy, isoquinoline, you could increase the rate by more than 2 orders of magnitude. So if you just change the pyridyl over here by methoxyisoquinoline, I go from 5 cycles per second all the way to 1,000 cycles per second. And that's basically because here I have a positive pi-pi interaction between the two pi systems over here. That allows me to put the two molecules together, the two metal oxide together, and that reduces activation energy so that it can go very fast. So that was our starting point. So we wanted to even increase a little bit more the turnover frequencies here. If you want to do, on the long run, what you want to do is light-induced water oxidation. You want to incorporate this metal with water oxidation catalyst into electroanodes and photoanodes for making devices. And basically, if you want to do that, if you look at the kinetics of all this process, the water oxidation reaction is the slow reaction. So we wanted to do things, one, increase the turnover frequencies if we could, and the second one is that when you're building devices, normally you only put it into a solid state. So if you put into solid state and you have something that dimerizes, you are in deep trouble, because basically once you put this ruthenium catalyst, for instance, into a solid support, into an electrode, it cannot dimerize. So a wonderful catalyst that works in homogeneous phase, if the mechanism is dimerization, when you put it into solid, it cannot dimerize. So it cannot dimerize, it cannot have this pi-pi interaction. So you end up with something that's wonderful in homogeneous phase to something that's not that good in heterogeneous phase. And not only that, but because the catalyst needs to find a higher energy pathway, it still can do water oxidation, but it needs to go to higher energy pathway and end up killing itself. So if you do a cyclic voltammetry of the catalyst anchored in the surface of an electrode, you see in this dashed line, that's the typical behavior of the catalyst in homogeneous phase. But once you cycle a second time, I'm sorry it's not clearly shown here, but you lose nearly 30% of the initial intensity, and if you keep cycling, the only thing you end up is with ruthenium dioxide. So we wanted to, one, get a faster catalyst, and second, to change the mechanism from bimolecular to unimolecular so that we could build devices that would last longer. So one of the ligands that we turn into is what we call the TDA. This is basically a terpyridine with a couple of carboxylates in the ortho positions of the pyridyls. You use a ruthenium source and you let this react. You end up with this octahedral ruthenium-2. This is low spin, high field ruthenium-2 diamagnetic. You have the 3 nitrogens, 1 carboxylate coordinated, and then you have, this is the crystal structure, you have 1 dangling carboxylate that is not coordinated at the oxidation state 2. So this is nicely diamagnetic, you can find this here. So you can take this compound, we can oxidize it from ruthenium-2 to ruthenium-3, we can get the crystal structure, isolate it, and characterize it. We can further oxidize it one more to ruthenium-4, and once we oxidize it to ruthenium-4, then the complex became 7 coordinated. So now all the ligands, all the atoms of the TDA ligand are coordinated over here, so we have the 3 nitrogens and a couple of carboxylates. And now we change the geometry from coordination 6 to coordination 7. Now this is a bipyramidal, a pentagonal bipyramid kind of geometry, and the crystal field that makes into that, it splits orbitals, the d orbitals in this way, so that the d, xz, and yz are degenerate, and being a d4, this is going to be low spin d4, and is diamagnetic, as you can see over here. But ruthenium compound with 7 coordinated, this is from a water oxidation point of view is useless because there is no way that it can make oxygen-oxygen bonds. So you can make a stable ruthenium-4 because of the strong electron donation of the ligands, but it's completely useless. But if you take this compound and you put it at pH 7 and you start cycling, the red trace is basically ruthenium 2 to 3 and 3 to 4. Those are basically, we can generate electrochemically or chemically, but there is nothing else going on. But the green traces is when you go a little bit higher in potential, then there is a new thing that starts being formed here, and that's basically a substitution of one of the coordinated carboxylates by an OH group. and this is transforming a useless compound into a wonderful catalyst. So once we make this OH group here, then we can go one oxidation step up, we'll make ruthenium-5, and this, under the right conditions, this is a huge electrocatalytic wave. This is the highest electrocatalytic wave I've ever seen in the literature, and we can reach turnover frequencies as high as 50,000 per second. So why we go that fast? It's basically because once we make ruthenium-5 oxo, then we have to have this water nucleophilic attack interaction. So oxygen interacts with the oxo, and you also have to lose a proton. So at the moment, at the same time you are making this oxygen-oxygen bond, you are transferring a proton to a neighboring carboxylate. So this intramolecular proton transfer at this transition stage is what reduces the energies of activation and makes the system extremely fast. So okay, so now we have a catalyst that is extremely fast. It goes water nucleophilic attack, and we can now put it into surfaces and do electroanodes and photocathodes. Photoanodes. So basically, one more proof that the key design strategy of this molecule was to have this hydrogen bonded and intramolecular proton transfer in the equatorial zone is we just make a similar compound where the aqua group was in the axial position and the rest of the TDA ligand is basically the same and the pyridyl is the same. So if you make this compound, basically this is still a catalyst, but it's a very, very poor catalyst. The difference between those two catalysts, just changing from the equatorial position to the axial position, we lose turnover frequencies by 4 orders of magnitude. So by changing the position of the aqua group, you can tune the reactivity of this catalyst. So as I mentioned, once we have this catalyst, we can change the axial position so that we can anchor on multi-wall carbon nanotubes, that we can put it in electrodes. We can do 100 cyclic voltammetries. We have no deactivation at all. We can do coulometry. We do more than 1 million turnovers. We have no deactivation at all. So that by choosing the right ligands and the right mechanism, the complex is very stable. We also put it into a photoanode. This is a collaboration with Nathan Lewis in Caltech. We used his very beautiful silicon powerful semiconductors that are stabilized by a layer of titanium dioxide. On top of this titanium dioxide, we put a very small layer of graphite, and then we put our nanotubes and our water oxidation catalyst on top of this graphite layer. So by doing that, then we could see very nice, this typical cyclic voltammetry. This is in the P+ silicon electrodes that behave like a conductor. This is like a control reference. And when we use the semiconductor, we had these very nice photocurrents that were shifted the potentials cathodically by 240 millivolts, and that basically were telling us that the two elements were working properly together. And with this arrangement, with this kind of arrangement, we could sustain, we could do a chronoamperometry at 1 milliamp for more than 1 hour, and this type of device allows us to check exactly what happens at the beginning, in between, and at the end, just by doing a cyclic voltammetry. So basically, this is allow us to really check that the nature of the catalyst didn't change over the whole experiment, and it was not ruthenium dioxide that was doing the job here. Okay, so this is the end of my ruthenium. So now I'm going to go to the third part of my talk, which is we wanted to see. I mean, we knew how to make water oxidation catalysts, and the question was, can we go back instead of doing water oxidation? Can we turn it into oxygen reduction? And we started with this, what we call the RuHBPP. This is one of the early complexes we work with. This is inspired in T.J. Myers' blue dimer. We just changed the oxo bridge by this bridging HBPP ligand here that allow us to put a couple of rutheniums. And this is the third P that completes the coordination sphere. And then we have two oxo groups or aqua groups that look into each other. So we did a whole bunch of work with this guy, but mechanistically we end up with this scheme. The third P ligands are not shown in this scheme, So we had the ruthenium aqua groups. We could remove 4 protons and 4 electrons. We could see that chemically, electrochemically, and then we generate this ruthenium 4,4-oxo. And then we had an intramolecular oxygen-oxygen coupling that we can follow by mass spectroscopy. So we knew exactly that that was an intramolecular interaction. Then aqua substitution at one of the rutheniums generated that terminal peroxide that finally end up making oxygen. So the question is here we go clockwise. So what should we be doing with this type of system so that instead of going clockwise, we want to go anti-clockwise? So the first thing we did is we took all these arrows that go in this direction and we just changed the directions. And everything that goes in now goes out, and everything that goes out previously now goes in. So basically, we wanted to start with ruthenium-2 and do oxygen activation and go the other way around. But this doesn't work at all, so then we decided to turn into ferro transition metals like that at low oxidation states, they are highly sensitive to oxygen. So we went into a cobalt, so we made exactly the same catalyst with ruthenium, with the HBPP and the terpy, but changing the ruthenium centers by cobalt. So we make this cobalt-2 oxidation state 2 bis aqua complex. We can isolate this, and we can isolate under nitrogen atmosphere, and the moment that this sees oxygen, immediately makes the peroxide very quickly like a shot. So this is the crystal structure of the cobalt-cobalt with the peroxide over here. This looks exactly the same as our ruthenium compound with peroxide with DFT. We never have been able to isolate, but we compare the peroxide with DFT is basically the same. So once we reach this peroxide, we can do 1 electron reduction and make the cobalt-oxyl hydroxo, and a second reduction takes back to the cobalt-3,3 bis hydroxo, which we also have a crystal structure. And this is further reduced by a couple of electrons from 3,3 to 3,2 and 2,2. So this is oxygen reduction all the way to water, 4 electron reduction of oxygen to water that we could show that it worked catalytically. So the oxygen reduction here we show we could do that way. And if we take now the peroxide, this is one of the intermediates, exactly this one here, that then we further reduce. If at this point, instead of reducing, I can do oxidation, and that's what I'm showing here. This is the cyclic voltammetry of this peroxo compound. I can do 1 electron oxidation to make the superoxide, and the second electron oxidation just goes to generate dioxygen. We show that by resonant Raman spectroscopy. We prepare the peroxo compound with oxygen 16, oxygen 17, and oxygen 18. And basically, this is the typical textbook-like peroxo for resonant Raman. And once we remove an electron and we make the 3,3 superoxide, then we have the typical vibrations around 1,000, 1,100 and with the right shift. So basically, what we are proving here is that from the peroxide, we go to the superoxide, and once we remove 1 more electron, we end up making oxygen. And we follow this by mass spectroscopy. If we start with the label oxygen 17 compound, then the only thing we're getting is oxygen 34 from the initial compound. So basically, the summary is that we have a cobalt complex that can do, if we go to higher oxidation stage, can do water oxidation. If you go to lower oxidation state, then there's oxygen reduction. And this is a bit of a summary. And this is basically what nature uses, the same type of trick. This is an example of the chloride dismutase. This is a protein that makes oxygen-oxygen bonds from chloride. So it takes iron 3, it reacts with iron 3 heme protein, it makes this iron 4-oxo, finally an oxygen bond and releases oxygen. But the oxidation state of iron, it never goes down to 3, lower than 3. So it cycles from 3 to 4, but never lower than 3. If you go to lower than 3, then you go to cytochrome P450 type of compounds. And then once you are at oxidation state 2, then you go the other way around. You go to the superoxide and one more electron to the peroxide, and finally oxygen-oxygen bond breaking. Okay, so basically that's all I wanted to talk about. This is a summary. If you play with the right ligands, you can have an idea of all the different intermediates that you can find, and you can direct to one type of mechanism or another, depending on how you design your ligands. And this design is important, especially if you want to build devices for like electroanodes or photoanodes or for whole electrochemical cells. I think it is also curious to use different transition metals, because the water oxidation mechanism that I show you with the ruthenium is radically different from the cobalt. In the cobalt case, the cobalt centers, they never change oxidation states. So we do water oxidation, removal of 4 protons and 4 electrons, and the cobalt never changes from oxidation states. We are only oxidizing the oxo. Whereas in the ruthenium case, it's a combination of oxidation of ruthenium oxidation states and the oxygen. So finally, this is the people that work hard at ethics, so I can give you nice results over here. So those are the guys that really are credited for the work. We collaborate with the people. I show you around, plus a whole bunch of other people that want to work with us around the world. And finally, we get money from the local, the central, the European, and even from ACS Petroleum Research Funds from the US. So just I'd like to finish by thanking you for your kind attention.
Thank you very much. An excellent talk. We have a few questions.
Thank you, Tony. A very nice talk. My first question is, when we evaluate catalyst, we pay more attention on the onset potential because it's more related to the both the thermodynamic and the kinetics for the catalysis. So, how about your ruthenium BTA compared to the ruthenium BDA, the onset potential? Can you give a comment?
Potential of the BDA has a couple of carboxylates that's bonded to a ruthenium center, and when it gets activated, you have an additional OH minus there. So the TDA, it has 2 carboxylates, but at the active site, one of the carboxylates that just goes out. So basically, you have 3 nitrogens neutral plus 1 carboxylate, 1 OH. So you have 1 less negative charge. So that means the over potential is a bit higher. We go all the way to 500 millivolts, and this is one of the things that we're working right now, try to get catalysts that work through the same type of mechanism, but they have the sufficient charge so that we can decrease the redox potential. I can't remember exactly the values. I mean, at pH 1, the BDA, it has an over potential, if I remember properly, 200 millivolts. But at pH 7, I think the potential is a bit higher.
And the second question is, you mentioned the top of your catalyst is, I think it's, I remember it's 10,000, right, per second.
Yeah, it's about 10,000 at pH 7. It's about 50,000 at pH 10.
Yeah, it's calculated from the electrochemical, the CV, right?
Yeah.
Yeah. And in your recently published the GX, you put the catalyst on carbon nanotube and coupled with the silica anode, a photoanode. And the tail number you got is 60,000, right?
That's turnover number, yeah.
Yeah, but you got that is in 2 hours, right? After 2 hours, but the top is it's 10,000 per second. Yeah. Can you explain a little bit?
This is not the only.
Can be finished in 6 seconds.
Yeah, but this is not the only reaction that is occurring, right? When you shine light on the silicon semiconductor, then you have charge splitting, you have charge recombination, and then you have water oxidation. So there's a whole bunch of things that do go on around there. So this is, you cannot calculate the turnover frequency of your catalyst just based on the whole device. I mean, there are a whole other things coupled here that can, I mean, the quantum efficiencies are not 100%, right?
Okay,
thank you.
Theo, it's a question.
So, also related to the question of over potential, I was wondering if you have a version of the scalist that's a derivative of the compound you showed early on with a dipyridyl benzene, and so that will add a negative charge on the ligand, and perhaps make it easier to oxidize.
Yeah, that's basically what we are working. We have published recently a paper in ACS catalysis where we correlate. I mean, all these type of catalysts, you normally, to make them active, you need to reach ruthenium 5. So basically the redox potential between 4 and 5, that's basically telling you the over potential that you're going to have, because that's the maximum potential, the minimum potential you have to reach to see water oxidation. So we had looked at the literature, and basically there is a direct correlation between the number of anionic groups that you have into your ligand versus the 5-4 redox potential. And it also depends on whether the complex is 6 or 7 coordination, because if you reach 7 coordination, you have one more base there giving electron density. So there is very nice correlation. So now we're working on getting over potentials around 150 to 100 millivolts. We have this, but we haven't published, and we are working on that. It's not 100% solved. Let me put it this way.
I might be not missed something because I was out of the room for a while. But when you have the bi-ruthenium complexes and you're getting these extremely high rates of, fantastic actually what's been achieved. But is that mainly down to OO coupling? We're going to call it OO coupling for the minute, because of course we don't know what to call it. But yes or no?
Well, in these compounds, the ones we have shown you, the oxygen-oxygen bond formation is the rate determining step. So once you reach ruthenium 5, the slow step is the oxygen-oxygen coupling. If this is your rate determining step, anything that lowers the energy of this oxygen coupling is going to be good for your catalyst. And one of the important things when you do this oxygen-oxygen bond is that the water that's coming here, it has to get rid of a proton, because you're going to end up a hydroperoxide. So that's why the intramolecular proton transfer helps a lot on reducing the activation of energy.
That's a key thing.
But if your rate determining step is not the oxygen bond formation, then obviously that doesn't help.
When you come to a mono metal ruthenium complex, of course, unless you get aggregation, now you've only got one metal. I mean, in the other case, you have two metals, an oxide, and bang.
Yeah.
So that makes good sense. But when you come to a mono, we're going to talk about it a bit later, I suppose. Now, this is a different situation where a nucleophilic attack mechanism is that more probable? Because
Well, I think it depends on several things. The RuBDA, the one we collaborated with Li Cheng, it basically likes to dimerize. So it depends on a lot of the electronic structure of the ruthenium 5 ox or ruthenium 4 oxyl that you make that. If this has a large tendency to dimerize, then it goes dimerization. But the pathways for dimerization and for water nucleophilic attack are not that far in energy.
Of course, if you get dimerization, you get two metals close together again and you're back in the same situation. But if you don't get that dimerization, you've got a fixed system with a mono ruthenium content, nuclear content, then the mechanism you do get does work.
Yeah, the
mechanism looks to be, from what I've read your papers and so on, a water nucleophile attacking a highly, often a ruthenium 5 oxo. So
we've basically done what you just mentioned, and we take a catalyst that likes to dimerize in solution, and then if you isolate it and you put it at the surface of electrode, it cannot dimerize, but you still can see water oxidation. So there is another pathway that does water oxidation based on water nucleophilic
attack. You
attack.
guys have done a fantastic job. Part of your drive is to get very high turnover rates. So you just go for the best thing you can find.
Exactly.
And the bimetal centers or aggregated centers are giving higher rates. So that's fair enough, nothing wrong with that. But in photosystem 2, we don't have dimerization. We have in fact two metals, but one of them we have two as far as I'm concerned. We have a manganese and a calcium. We have a bimetal center. And the calcium is extremely good at producing a nucleophile or hydroxide for attack onto a highly electrophilic oxo. That's all I'm saying. So it's slightly different. the radical coupling the coupling mechanism could have been adopted and had been suggested in the past for photosystem 2. But when one looks at the structure now that we have, well, not everybody's going to agree with this.
Well, yeah, I was going to say, there's a huge debate.
I'll stop there.
I have you for
I'll stop.
Let's just, one more question, Holger. And,
Yeah, it's a short question, but a bit related. You had this impressive results where you showed that the rate of turnover is increasing a lot if you have a kind of an acceptor base, a carboxylate, taking a proton. And this is, of course, an attractive option also in photosystem 2. And I was wondering, is there any kind of kinetic signature? Do you have a significant kinetic HD isotope effect, for example?
We haven't looked at that so far. The problem with this one to make this nice kinetic work is that we never isolate the catalyst totally pure. What we do is we use the precursor catalyst, which is the one before we have the OH, and this is in equilibrium. So to do good kinetic work, and this is something we are working, is we have to isolate 100% the initial compound, the catalyst, and then, because if you don't know exactly your concentration, it's going to be difficult to control your kinetics.
Means right now the rate limiting step is not the OO1 formation step?
No. What I'm saying is that when we perform kinetics, we need, at least the way we do it is we need to know exactly the concentration of our catalyst. And at the present, we have, when we generate our catalyst, is a combination of precursor plus the active catalyst. And this is in equilibrium. And I think for the kinetic perspective, you want to have 100% pure catalyst and then all your kinetic analysis. We generate different relatively similar catalysts as the ones I've shown here, where we can fully isolate 100% the catalyst. And this is something where we will go into, but this is something we should certainly go into.
okay, let's thank Tony again for a really great talk.